האסיסטנס אנחנו כנראה לא רוצים, נכון? ולכאורה זה מוקלט. אוקיי, אבל אין אף אחד בזמן. Okay, so everybody is comfortable with Hebrew? You don't speak Hebrew? Okay, so English. Oh, please say it fine. So we can start, yes? So my name is Rami. Oh, maybe. So it's going to write mail. So I don't have opt-out, but we just can arrange a meeting each time you want. Feel free to write mail, feel free to call, say from 10 a.m. to 10 p.m. And I will usually not answer. Oh, I might not answer right away, but I will fight for that. I'm not answering WhatsApp usually, so I see them week after you send them. So if you want to send a message, use a mail. If you want to talk to me with the phone, or use my name, and we can fix it all. So free. What else? We have a TA. It's not here now. Shachar Dagan, and I think it's written in the website when are the TA sessions. And the grade will be based. There will be no grade, just pass fail, one big grade, and based on your home assignment, which you would grade. We need to talk about when are the deadlines. He will tell you, but just submit on the time because otherwise it will not be graded. And then you get the credit. Okay, these are all the general stuff. Okay, so where is that? What is category theory about? So here is a possible motivation. We go back to 19th century. There was this Felix Klein plan to study geometry. So at that time, just people started to realize that there is more geometry than just linear geometry. So it's probably started with Gauss spherical geometry. So of course, people knew that we're living on a sphere, but Gauss started to ask questions how we can realize that we're living on a sphere without getting out of the sphere, without looking at the sky, just by measuring Earth, and that the Euclidean axioms, usual Euclidean axiom doesn't work. The sphere have a triangle where all the angles are 90 degrees. And then I think slightly after that, or maybe parallel, that Lobachevsky just played with the previous axiom. So yeah, I'm oversimplifying the history because the class is not about history. And so that you can just change axioms and see many things will work. And so people start to ask what are the limits of this thing, and of course at that time already it was after Riemann, so we made very general framework for different geometry, Riemann geometry, etc. But Klein had this idea that instead of studying geometry, we should study books, because each geometry has its own book of symbols. And so Euclidean geometry, we have this transformation of the plane, you can shift, you can rotate, you can allow and not allow configuration depending on the place. Now spherical geometry, we can rotate the sphere. Hyperbolic geometry with its own rotations. And now you can add some new symmetries, and then you just relax the geometry. They want to do affine geometry, so you can make affine transformations that are not preserving distance anymore. So it means that you basically cannot use a compass anymore because it doesn't make any sense. There are no distances, but you still can use ruler. Yeah, so for clearly build everything on ruler and compass, so you can just throw away the compass and see what you can do with ruler. This is affine geometry. So symmetry is you cannot talk about angles anymore, about distances, but you still can talk about lots of stuff. And the projective geometry, more symmetry is allowed to interchange infinity with other points. So this was its idea, and you indeed can study lots of kinds of geometry this way. And the problem is that it doesn't work in general. And the easiest example you can think of, you can take a nice sphere, bit of metal, and take a hammer, hit the sphere, and no symmetries. So everything breaks. So if we would try to study this thing using symmetries, we would get the same as if it was just one point. And certainly sphere, a hammer sphere still have very interesting geometry. So as I see it, category theory is basically a way to fix this problem. So what you need just to relax a little bit the notion of a group, and then it suddenly fits not only to any kind of geometry, but more or less to any kind of mathematics. So any kind of mathematical theory can be studied using these symmetries if you allow a wider range of what we call symmetry. So usually in group theory, so we have this abstract notion of group, but it's always coming from, usually coming with main equation. It's group transformation of some object, like geometrical object, or historically it started with break object and field. So, but what are the transformations? They should preserve the geometric structure or the underlying structure, but they also have to be invertible, but you want to be. So one first thing that you can do, you can solve this assumption out. I'll just talk about transformations that allow not to be invertible. So if you try to axiomatate it, you just erase the axiom of any element here. Inverse, and you get monoid. And the next jump is slightly harder, that you don't consider symmetries of a single object, but also symmetries or relations between different objects. So transformations that don't start at any the same object, but have different objects. And basically, when you formalize it, which is slightly harder than just erase one axiom, you get a notion of category. So you can think about the notion of category as what group try to do and sometimes succeed and sometimes not. So now they basically can do it for every theory. So probably the main way to think about category theory is a theory of theories. So for any mathematical theory, we have some objects. So we have linear algebra. So we have linear vector spaces. So the collection of all vector spaces form a category. And like maybe the simplest mathematical theory, empty theory, we have just study sets. It's not that set theory. Set theory usually doing something else. So the collection of all sets will be the category of sets. And groups, which may be invented to study symmetries of objects, but we can study groups by themselves, they form the category of that's it. So this is maybe the first main motivation to the notion of category. And I will define it. And second, you just can think about it as a next level of abstraction, say after a set. So we probably the first level of abstraction in mathematics was numbers. Yes, so it's all something abstract, not concrete, but people understood what are numbers many years ago. And then they said, okay, maybe we can do some operations with numbers, so we're not interested in single numbers anymore, but in collection of numbers like natural numbers, integer numbers, rational numbers, etc. So the next level of abstraction was some objects which are based on sets like rings, fields, etc. And now you can do, okay, let's do collection of all fields, collection for rings. So again, we go into this idea of category. And now the third approach to, or the third way to think of categories, and again, I'm going back to generalization of groups, and the same with groups. So we start with studying singles of objects, but then group theory have a life of its own. Have some internal structure, some combinatorial objects, notion of a group. And in the same way, we can also study category theory. It's less common. It's not like the main way you use it, but some examples of categories are more similar to some combinatorial object, like group or like graph, than to collection of all mathematical objects of certain type. And more or less, it's like with a group. So you, at the beginning, you should think about the group as a group of symmetry of some object, but you're also allowed to think about groups like something that you by itself and nothing to do with other things. Okay. Any questions before I go to the definition of category? I will put it silent. So let us start with the definition of what is called small category, which is more or less, for this course, it will be more or less the same as general. So for defining a small category, we need two sets. Oh, no, let's do it different. We need first one a set of objects, which we'll call OB, the collection of objects in this category. So if we're doing, say, category of groups, then OB will be the collection, the set of all groups. And yeah, I believe you all know set theory, and you know that I'm not allowed to say set of all groups, so let's know it for now. Maybe we'll come back about it. Now, for any two elements in this set, we'll have to define a new set, or right, which is another set, which we think of as the collection of transformation between the object X and the object Y. But again, like in group, the abstract definition of category does not require that X and Y will be some physical objects, so it will be some sets, and does not require that more from X to Y, except more from X to Y will be actually sets of transformation. It can be just some abstract set.
Thanks. Yeah.
A bit louder?
Why to suppose that the objects in the set? I mean, for set, it's not almost actually.
I will go to this point. So, as I say, what I'm defining now is called small category, and we'll discuss the point that you mentioned. Okay, so we have more xy, the set of morphisms from X to Y, and we can have more yz object, and now we have another map, which we call composition, which is coming from here to more x. And again, we should think about this map as composing transformation. So if we have some transformation from X to Y and transformation to Y from Z to Z, we can compose them. But this is the way we think about them. They don't have to be, this map doesn't have to be defined this way, because these sets can be just absence. And now, okay, I can make another thing. I have the element identity X for any X in ob, more, which is element in more X's. We should think about it as identity transformation, just each element goes to itself. And now we have axioms, and you can guess of these axioms. Very similar to group theory, but instead simpler, just like for noise. So first of all, composition is associative. So if we have X, Y, Z, W, we need 4 elements to talk about associativity. And if we have morphism F, so instead of writing F is element of X from X to Y, I can write arrow like this. Like F is a map from X to Y, but it doesn't really have to be a map, just the element be small. F, G, H. Then the composition, we can take how do we do composition? We always using the notation backwards, like the composing function. So first apply F, then apply G. And this composes H. So this notation G compose F. I should write it. G compose F. By definition, we mean apply composition to the pair F. Reversing the order. Should be equal to H composed with G. This first axiom and the second axiom X composed with F equal wait. F when you compose the identity, you change nothing. It will be tautology if maps are just maps. And basically, this is the definition of small category. So why I'm saying small? Because I require that the collection of all objects to be an actual set. Like in most useful examples, so at least at the beginning, the first examples come to mind, they will not be small. Because the collection of objects will be, for example, a collection of all sets, collection of all groups, collection of all topological spaces. So neither of these is going to work. How to fight with it? So first of all, like in set theory, there is this notion of classes. So you can build set theory not only with sets, but also with classes, which are much wider than sets, which are allowed to be the class for sets, the class for groups, etc. So this is probably the most, I don't know, if you just want to do it right, this is the way to do it. You're not discussing small categories anymore, you allow orb and more to be, orb to be arbitrary class. Usually, it depends also, some textbook define category in a way that orb is a class and also more between two objects is a class. But usually, you don't need it, and more between two objects is just a set. But also usual examples that you will see, more would be an actual set. But for object to be a class, and you can define everything, but then you need to know this set theory with classes, which most people didn't study because they just don't teach in first year, and then if you don't do set theory, you never go. Okay. Another option is just to say, okay, let's fix some very, very large set, and we'll never consider like very big categories. We'll not consider a category of all sets. We'll consider a category of sets which are subset of this huge set. When we fix huge set, we call it universe. And sometimes we want it to be like really large in the sense of set theory, like larger than any cardinality that you can usually imagine. But for most applications, you don't really need it. Once you can do it for any set, you can just change the setup for whenever you need. And then you can just use the classical set theory with classical notion. And maybe the most popular way to deal with this problem is just to ignore it. So if you look at most papers, most textbooks, well, textbooks maybe not, but most papers using category theory, and they just ignore this issue, talk about categories, not about small categories, but they just also ignore it and don't do stupid things that will give you Russell paradox, etc., and you will probably be okay. Of course, it's not a good way to verify completely that all what you're doing is correct, but since most of people that use category theory, they don't actually work in, they just use it. So yeah, you can get away. And I think this is what we mostly will do in this course. Maybe at some point, some problem will appear. Any questions? I forgot to say in general, feel free to ask questions in the middle of explanations. Try not to interrupt in the middle of the sentence, but feel free to ask questions as long as it question for like when you try to understand what's going on. If you have more questions, like how it is related to something else, so great question, but then this will in the times when I ask whether there are any questions then. So now it's perfectly okay for any question also about related stuff which is not happening. Okay, so let's start with examples. One example of the category, and now we will. Well, the examples will usually be of large category, not small category. But is a category of sets. So objects are sets, and morphisms are just elements. And composition is just composition. So this is the most basic example of category of set. If we consider category as an analog of group, and then as the most basic example of group under this point of view will be the group of permutations, and as the most basic example of category will be the category of sets. Next example, go. Another thing we forgot to say, I have like rather severe dyslexia, so I would have lots of spelling mistakes. You can either know them or correct me both the time. So or groups, what are the categories of the objects are groups, the collection of our groups. Morphisms are just homomorphisms of groups, maps which preserves the multiplication, and as usual, compositions of compositions. And now another example, which take you to a slightly different point of view on categories, is a single group. So once you have a single group, you can think about this group as a category. And now we don't think about a category as like objects or some physical objects and maps or some isomorphisms or some maps between them, transformation, but we just like abstract things. So if we have a group G, we can define ob to be singleton, and more between the only object to itself, because it's the only mode that we need to define, G. And the composition is just the multiplication in G. And the identity map is just the equal element in G. And this satisfies the axioms, and you see that here the map doesn't have to be actual transformation. Another example, abelian groups. Objects are abelian groups, and morphisms are homomorphisms of groups. And now maybe I want to concentrate on these three examples, and you see that they're all somehow related. So we started with sets, and now here we kind of choose some of the sets, which are groups, and choose some of the morphisms, which are homomorphisms. And here we just choose some of the objects, some of the groups, but didn't change the notion of homomorphism. So abelian groups, the category of abelian groups, is a subcategory of the category of groups, and moreover, it's what's called a full subcategory. So what is a full subcategory? When you choose some subset of objects and say, okay, this will be my object, but the morphisms are the same as before. You can always do it just with any choice of object. What are the relationship between this category and this category is a little bit more complicated. So there is a general notion of subcategory when you choose some subset of objects, but then you also choose subsets of morphisms. So intuitively speaking, you can think of groups as a subcategory, but not full subcategory of the category of sets. Formally speaking, it is wrong, because group is not just a nice set. Group is a set with additional structure. The same set can have different group structures. But this thing can be corrected. So at some point in the course, we will explain why it's basically okay to think group sets are sets. Okay, what we also have here. Okay, so we can just talk about modules over a ring, vector spaces over a field. There's a collection of all posets, partially ordered sets with maps which are reserved in the order. And here is another example of a category which is more of combinatorial nature. A single poset. A poset is partially ordered set. A single poset can be considered as a category. How do we do it? We say that the set of objects is our poset, and morphism between two elements, either one of morphisms or none at all. So more A B is equal to 1 if A equal to B, and empty set. So how do you compose? So there are not too many options. If you have two elements to compose, and you just compose them and get a single element in the target, and it's okay because you can do it because the order is fine. And the identity element is the identity morphism is just a single element with A. So so category can be thought for one hand as a generalization of group, because we have this example of a book, and maybe the other extreme is a generalization of poset. So a category looks like a poset if for any two elements either one map or zero maps. Again, formally speaking, it's not really true that any category which is like this is obtained from poset, but intuitively and in some point I will explain formally what does it mean. You can think about any category that satisfies the condition that have either one or zero morphisms as a poset. And here, if we have just one object, then the category is actually coming for a group. Because this has two extremes. Okay. Now we have the category of topological spaces. So do you have a guess what are morphisms in the category? Continuous maps. Topological space, continuous map. Yeah, so it's one of the cases. It's not immediately clear what are, like, if you just axiomatically define topological spaces, open set here. So why you define continuous mapping, or why you define morphisms in this way? Maybe first reasonable guess will be maps open maps that map open set to an open set. But since your aim in studying topology is defining a continuous map, and the topology is just a tool, so this is actually, so you want to define theory of topological space with continuous topological spaces. And again, you can think about it as subcategories. So most of the categories we will discuss kind of nature subcategories of sets, although formally they are not subcategories, but like sets will allow we allow only part of the model. And the way to do it is to put additional structures. And another example, as before, I think the topological space. So if you have topological spacing, we can also think of it as a category, or we can create from a category. The way to do it, you consider the poset of open sets in this topological space. Okay. As we said before, any poset gives you Okay, what's an more interesting example? Now, often things that you like to do in math is combining different structures. So, nice example is the topological space that happens to be also a vector space. This is called linear topological space. So we're all familiar with the notion of linear topological space. That's addition and multiplication by scalar has to be continuous. You usually work over some very fixed field, usually R or C, so we have nice topology there. You have linear topological space or linear vector space. So topological vector space, we usually call it. And the maps are continuous linear maps. And this gives the category of topological vector. Inside topological vector space, we have many interesting subcategories. So you probably all heard about Banach spaces. Everybody know what is a Banach space? So this is a subcategory of topological vector space, and it is a full subcategory. Usually, when we talk about Banach spaces, we talk about Banach spaces, but morphism between them just have to be continuous maps or cumulatively bounded linear bounded maps or linear continuous maps. So theoretically, you could have thought about different category of Banach spaces where the morphisms have to preserve the norm, like being isomorphic. So usually when people talk about the category of spaces that mean it, if they want to mean it, they talk about category of Banach spaces with isometries, and it's rather there. Inside the category of Banach spaces, you have the category of Hilbert spaces. And here, there is no one standard notion of what is this category of Hilbert space. So the objects are Hilbert spaces, but what are the maps? And often people consider maps to be all continuous map, but sometimes people consider maps to be isometries. And if people want to distinguish between these two notions, so they invented the notion of Hilbertian space. Though I think it's less common because so today it's less common because often people say just Hilbert space meaning what for Hilbertian space, but for this discussion it's very convenient because so Hilbertian space are Hilbert spaces. The category of Hilbertian space and the category of the objects are Hilbert spaces and maps are continuous. And for the sake of this conversation, the category of Hilbert spaces are the category of the category whose objects are Hilbert spaces and maps are isometries. So this is a full subcategory, and this is not. But it doesn't have all the opposite of full subcategory, and so it's called spanning subcategory, because it have all the objects, but not all the. Okay. Another examples. Let me see. So, who knows what is an algebraic variety? Oh, so most of you, but not all. Yes. So we will have many examples like this in the course when you don't really need to understand all of them. We'll say no. Then the example. So I will just briefly say what algebraic varieties or some of them. So if you have you fix some base field, let's take C, usually algebraic field, and assign algebraic varieties are subsets of C to the n that are defined by collection of polynomial equations. And using this notion, you can define more complicated notion of general algebraic varieties. So most of you know, you can use it. If you don't know it, so what are morphisms between algebraic varieties? There are many definitions, but if we start with defining algebraic varieties and want to define in this way, then the convenient definition is like this. We have two affine algebraic varieties, and morphism between them is a map that can be extended to a map like this. And so when I say can be extended, so any element in X is element here, so map to here, and if we start with element to X, we have to follow the element to Y. So it can be extended to a map like this, such that this map is given by polynomial, n polynomials in M. Now note that two different maps like this can give the same map here. But the morphisms we just the map here. We don't need to know how you extend them, we just need to know that you can So yeah, so this is a particular final algebraic varieties, and you can use it in order to find the particular or algebraic varieties. So the objects going to be distinct and algebraic varieties and morphisms are map surface. Also, so what is manifold? CNP manifold? Do you know? Who knows what is manifold? Okay, everyone. So the relation for manifolds is forms category maps are smooth maps. So we continuous map that have the infinity memberability. So one way to define it when the map with x and y is smooth is when you take a smooth function on y. So this is usually easy to define for smooth function on y. When you compose it with this map, you get a smooth function. Here define smooth function to our just the function which is smooth on any map or atlas or whatever the function of smooth manifolds you choose. Metric spaces. So metric spaces again give us lots of dilemmas. How do we define the category of metric spaces? So one way to define it, objects are metric spaces and maps are is a nice way, but you don't really get the feeling of what you can do with metric. So what you can do with metric, like what other categories you can go to another extreme objects are metric spaces and morphisms are just continuous many. But this is more or less the same as to just say you consider topological space which have a metric. So metrizable topological space. It's not formally it's not the same category, but they behave very similarly. We start on sometime. So things that you can do in between is you can talk about Lifshitz maps. So maps that can change the metric, but in a bounded way. In this case, in this way, you remember some part of the metric, but you do allow some changes, so to have more different objects. This is metric spaces. Okay, so maybe now the time to define over to the. Can I switch on the air conditioner? Or it's already on? Is it on? אני לא מרגיש ככה. טוב. אוקיי. Okay, so if we have some category C and some object at C, we have the notion of the over category. So it's a category, and we define it in the following way. So if I want to define a category and say what is org and what is more, so I say org of the category is just a set of objects. The collection of all papers like this, y maps or perfect y maps to this. So y running over all objects of C, and phi running over all morphism between y to x. And maybe I would write it like this. So this way it's called over category because we think about y upstairs and x down. Not very good reason, but sorry, x is an object. X is a fixed object in C, and here the collection y and y ranging over all the objects in C, and phi ranging over all morphisms from y to C. And now what is morphisms? Morphism between y to C, y to x, and y prime. So this is a collection of all diagrams like this. Very what is diagram in general, but this you can easily understand and give you. So when I say all diagrams, all community diagrams like this, so I need to explain what they mean. So I actually then go on the maps between y to y prime because everything else is already fixed, already given. And the fact that this diagram is commutative, such as the diagram is commutative, I don't write it, but the fact that the diagram commutative means that for any two objects in this diagram, no matter how you go from one to another, you get the same morphism. So in this case, there is only one case when it's interesting. So you can go from y to x directly by phi or just like this. And you have to get another option or more, the same morphism. So instead of just saying the diagram is commutative, I can just write this. You can first apply mu and then apply prime, or apply just all the diagrams like this, such as this equal to this, and when I say all the diagrams like this, it's just being automatic. So this is called over category.
So all the morphisms are used.
What?
The morphism
Are always used, but that's how it's listed. Yeah. So yeah, so it's again can be sort of a subcategory of the original category, but it's not really the case because we have this matrix. So you can think of it like this. Okay, so using this general notion of a category, you can define interesting categories, usually in geometry. So why it's called over category? It's the main intuition comes from geometrical categories, like category of manifolds, topological spaces, etc. And then you actually want to imagine why some spaces being over X, so the map from Y to X, you want to imagine it to be the projection. And then for each point in X, you can consider its fiber. So fiber is per image of a point, but why it's called a fiber? Because you imagine like Y like a large thing which is constructed from small fibers, and each fiber led to one point downstairs. And you can think about objects in the over category of X like families of objects in C. You have notion of points, so for any point in X, you can consider it per image, which is an object C. So again, not all doesn't work always, but it can work. So for example, for topological spaces, and these are families of objects in C, which are parameterized by element in X. So this is the equation for the over category. And usually you don't want to consider just all the maps from Y to X because this would be like weird families, but you want to look about on some subcategories of this over category. So in topological spaces, a nice subcategory will be gradients over so fiber bundles over. So what is a fiber bundle? Fiber bundle over X is an object in the now we're talking like now we're talking in of topological spaces. So X is a topological space, fiber bundle over X is an object in the over category of X, in from Y to X, such that locally it's isomorphic to a trivial bundle. So I said many words which I didn't explain. So first of all, what is trivial bundle? We can take X times Z. This is objects of the over category of X. So what is isomorphic? So I didn't say what is isomorphism in a category. I should have said in the beginning. That's not very fact category. Isomorphism is a morphism from X to Y, say, and another or such that there exists another morphism. See? Such that both of the compositions are equal or identity. So this should be identity where first I try to see, so this should be identical on Y, and this should be identical. If this important definition, I should have said before. And in a category, a morphism is called isomorphism if there exists, if it's have an inverse from both. Okay, so the trivial figuration is map like this. We can say trivializable figuration. Oh, a trivial object means over category is a map like this. A trivializable object means over category is object in the over category which is isomorphic to an object like this. So what does it mean? It means that we have isomorphism like this, such as the diagram is commutative. And this we can do in anything. Yes.
You can say, it means you have a local isomorphism.
Yes.
What's
in a
that?
moment. So until now we can say it in any category. In any category, we have notion of what is meant to be trivializable object of the over category, just isomorphic to object like this. But in category of topological spaces, we can say more things. So we can say what will trivializable, which is exactly called fiber bundle, or sometimes figuration, but usually often figuration with something else. So I will try to remember to say fiber bundle. So what it means locally. Locally trivial or locally trivializable. So an object in the over category is locally trivializable. This is just in the category of topological space, not in general. If this could cover I open cover such that U is so yeah, answer the question. Okay, so this is called a fiber bundle, and let's make 10-minute break or 15-minute break. 15. Usually we do 10 or 15. Yeah, you don't know, it's just okay. So let's do 15-minute break and. Buona iniziare pausa. Ok. Steramci. בקשה כללית, תנסו מי שצופר להזכיר לי להדליק את ההקלטה אחרי הפסקה וקצת שיעור, אני אעשה את פה גם, אז יש סיכוי שזה יקרה. הפעם הדלקתי. אוקיי. אז הגדרנו מה זה fiber bundle. מה? Sorry. So we defined what is a fiber bundle. Now we can define what is a covering space. Covering space is a fiber bundle with fibers are discrete topological space. So you will know topological space. So we have covering spaces. And now we can define what is a vector bundle. So we also can think about vector bundle as maybe no, I will take apart in this and define. Well, what's the what order to do it? Actually, we've talked about it before. No, okay, no, I think I can. That's one. I think I can do it now. Then I go back to it now. Okay, so I want to define vector bundle. What is a vector bundle? Bundle. Those are many equivalent definitions, so we'll start with definition which suits us now. So we want object in the over category of topological spaces, y to x, and with additional structure of a vector space on each fiber. At this point, I don't require any kind of continuity of this structure, just in each point, we have upload completely different structure of a vector space. But now, so vector space over, say, nice feet that we love, say R, which has topology. But it's fine, you mentioned vector space, so it always has a natural topology coming from the vector space structure, but I even ignore it. And now I want this thing to be locally trivial, but in the category of such object. So we can just as an intermediate step consider the category of objects in the over category of X with this structure of vectors. So what is the morphism in this category? It's just the morphism in the over category, which also on each fiber gives a linear one. And once we define in this category, we can ask. We have the notion of trivial vector bundle, minus V, where the topology here is the topology of the product, and V is a vector space, say 5-dimensional vector space over R, so it's a topology coming from the isomorphism with Rn. It doesn't matter what isomorphism we choose. And then here you have just a projection, and this is such an object in the over category, which with a structure of a vector space on each line. And now you ask as before with fiber bundles, you want such objects which locally trivializable in the category of such objects. So the map should be linear. And this is the definition of vector bundle. Okay, so now you also can define the notion of local system. Local system is something like covering space, but that you want the fibers to have a billion group structure. So you just repeat the same thing that we did with vector spaces, but for vector bundles, but with a billion groups. So the fibers should be a billion groups, and locally it should look like a projection like this, whereas instead of so local system. So okay, we want a we want it to be object in the over category, and we also want a structure of a billion group on each fiber, and we want it locally to be isomorphic to a trivial local system, which means X times a billion group with a discrete topology mapped to X. So this is called local system, which we will encounter in future examples. And next example related to the over category is the notion of sheaf. So who is familiar with the notion of sheaf? Well, so we will discuss this notion several times in the course. And historically, there were several definitions of the notion of sheaf. The first definition was by Leray, and then later definition by Grothendieck, and today the most popular definition is by Grothendieck. It's equivalent to the previous notion, but technically they are different. So in this course, since we want to discuss both of them and the fact that they are equivalent, we want to call them with different names. So we say we'll use the words Leray sheaf and Grothendieck sheaf. So usually nobody uses words because they're both equivalent and they're just sheaf. So today I want to talk about Leray sheaf. So what is Leray sheaf? In an object in the order category or something, right? So Leray sheaf over X is object in the order category, like this. And such that locally on Y, and this is just an opening bed. So any point in Y have a neighborhood, and such that the map of this neighborhood to X is an opening. And note that we don't require Y to be housed. And this might be a bit weird because usually everything X will be usually housed of topological space, and usually all the topological spaces are housed of. But here it's important for to get useful examples that Y is not housed of. Or not necessarily housed of. What?
I didn't get what kind of maps?
And what is the condition? That it has to be locally an opening bed. So as the but locally on Y. So before we was giving some conditions which are local on X. So locally is trivial, locally it's like trivial with fiber vector space, etc. Here locally on Y. So it means that any point in Y have a neighborhood such that from this neighborhood to X, the map will be opening bed. Opening bedding, it's clear what. Yes. Just one-to-one map, which is isomorphism to its image, like isomorphism in the category of topological spaces, meaning homeomorphism, and the image should be open subset. Okay, maybe in the language of all categories, so a map is open embedding if there is an open subset U, and here the map is just the embedding, so the fact that U is subset of X is the map, and isomorphism in the order.
Is it true that local immediate and Y and the X difference is only in subjectivity of function? The function selected and locally immediately by Y and in X is the same thing.
No, and because so when we do locally on X, we mean that we have a covering of X such as the preimage of each of the open sets set in this cover of X. Locally on X means that we have a cover UI such that the map from here to here will satisfy the condition that you want. And here we have cover of Y, not of X. So for example, if we have two copies of R next to R, so locally on the target on X, it's not an open embedding because it's not one-to-one if we take the preimage. But locally on Y it is. Okay, so any covering space is automatically a sheaf, a Leray sheaf. But of course, not the other way around. An open embedding is a Leray sheaf, but it's not a covering space. So covering space called locally trivial Leray sheaf. And most of you probably, or the people that raise their hand, familiar with other definition of sheaves, and you will see why they're equivalent, but it's first glance they look at us rather different. Okay. So I think we more or less finished with the first round of examples. Somebody want to discuss maybe other examples that I didn't give, but you like know some mathematical theory and you want to see how many theory on the Some other questions related to the examples? Okay. Now, one good thing that category theory gives you is a way to carry out some constructions that you do in one mathematical theory all over the mathematics. And there are several ways to see what is like the most basic construction in category theory, and because they'll start with some constructions and base our other construction on it. And maybe the simplest way is to is the notion of initial object. So what is initial object in categories? Initial object in and this will be now very typical in category theory. You usually when you have some construction, you can define it for any category. And define meaning that you describe it, and then it's in a sense unique, but not that you don't necessarily have. So for many categories, it will not exist. And for many, so initial object, not every category have initial object, but if it has it, obviously. So what is initial object? The initial object is if E E E E that so anyway, I have exactly one morphism from X to Y. So I say that if it so it not necessarily exists, well, we will find examples where you don't have an initial object. But if it exists, it's unique. In what sense? It's not really unique. You have many different initial objects, but or you might have but if you have two objects, X and Y, which are both or X and X prime, which are both initial, then you have a unique morphism from X to X prime because they're both initial. A unique morphism between X prime to X. And the composition of these two morphisms will be a morphism from X to itself or from X prime to itself. But you also have a unique morphism from X to itself. So it means it have to be identical. So any two initial objects have to be isomorphic. And moreover, this isomorphism is unique. So these are very often in category theory. When we talk about uniqueness, we will say that any two things will be isomorphic, and the isomorphism between them will be unique, or at least unique after you might require some others. And so, and this is so this is an notion of an initial object. Let's do examples. Somebody want to give a category that does not have initial object?
Non-empty set.
Non-empty sets. Yes, this is one. So usually in category that you find in nature, very often will have initial object. But if you do some combinatorial categories, for example, like a group G, you can make out of it a category, as we said before, and then it doesn't have initial object because there's only one object and there are lots of morphism between set to set. Or if you just exclude the initial object from a category, you usually would have initial object. So now let's do with positive examples. So the basic example of initial object is the empty set in the category of all sets. In the category of groups, what is the initial object? The trivial group. So there are no empty group, but there is trivial group and there is unique morphism. Category of topological spaces. What? Empty topological space, exactly. And some other fun way we can have vector spaces like groups, not really interesting. In the over category. Any thought about it?
Sorry,
Yes.
about topological spaces. What kind of morphisms do you have
in the category of topological relations, continuous map. And then the empty set has a unique continuous map from it to anywhere. In the over category, it's the empty over. The empty set in the over category. If you have, in fact, if you have initial category in your original category, then this initial object, then this initial object is also initial object in the over category. Okay, so now we can say everything again, and instead of asking Morphinum from X to Y, to talk about Morphinum from Y to X. And this will give me the notion of terminal object. But I don't want to say everything twice. So for this, we have the notion of opposite category. So what is the opposite category? If you have C, you have op C. And what is the opposite category of C? And the category of objects are the same object as C. And morphism between the two elements X and Y are the morphism in C, but in reverse from Y to X. So this again, an example of category which, at least at the first glance, does not look like something that encodes a mathematical object, because the morphisms are maps, but they are maps in the wrong direction. But at least on the technical level, it's very convenient to consider it, because it allows to say things only once and then say the opposite category. We just need to invent another name. So you have the initial object, the initial object in the opposite category is called the terminal object. And I will often call it a final object. This is a mistake, so I always make mistakes. So you know what. And what is the terminal object in the category of sets? What? A singleton. A set with one element, but there are many singletons. So there are many terminal objects, which is okay, but they're already morphic and the isomorphic in the field. What is the terminal object in the category of abelian groups or groups? Zigbee. We don't YP.
ZP.
ZP? What means ZP?
An abelian group is not subgroup.
This group?
Yeah.
So first you say for different pieces, all will be different groups, and they're supposed to be all isomorphic, so we have a problem. And in fact, it's have a subgroup, just only one or only two, and just a trivial group, because you not only have a map from trivial group to any group, you also have a map from any group to the trivial group. So trivial group. And this is an interesting question, how to define such objects in the categorical level. So maybe one way to try to do it is to talk about the category of fields. So the category of fields does not have neither initial object nor terminal object. You have the fields FP. So terminal objects there is no chance to have, because you don't really have the maps in the fields, because feature very, very large in order to refer to it, but also method embedding. That one. But initial object you could have, yes, somehow, because small fields can have many morphism forms, but you don't really have an initial object in particular fields, because you have different SPs, and they have no morphism forms to that one, and you have also a field. But once you fix a characteristic, so fields of a given characteristic have an initial object, and then the FP field version, the ZP you discussed, is an initial object in all the category of fields of characteristic P, and Q is an initial object fields in characteristic P.
Does the category of partial objects as an initial
Of all partial objects, yes. Also given partial object.
Yeah, this one.
Yes, this sometimes yes, sometimes not, depending on the partial order set. What will be initial object in the a partial order set? A strong minimum map which is smaller or equal to everybody else. And terminal object will be a strong maximum. Some of them have, some don't. Okay. So an initial object, terminal object, and we want to do more example of this stuff. Probably not now. And unless somebody wants to discuss an example of initial terminal object. And let's talk about diagrams. So I already started to talk about diagrams, but didn't give it.
You can say that the particular group is bigger than trivial, then
It doesn't have neither initial nor terminals. And yeah, and the category of a group, if you take the opposite category, you get the same group with multiplication reversed order, which is a different group, but it's isomorphic group. So there's really no difference. And but for most categories, for some categories, the opposite categories is equivalent to the original category. Oh, I didn't discuss equivalence yet. Right? And okay. Oh, I forgot one important example. Go back to it. So tell me now we'll discuss diagrams. I already discussed diagrams in one instance. So what is diagram in general? So first of all, we need to describe what is the shape of a diagram. So there are several ways to define it. So the simplest way is to say that we start with a directed graph. So we all know what is directed graph. And so what is diagram? Diagram is an assignment, diagram of a given shape gamma, an assignment that gives for any vertex of gamma an object in the category, and for any arrow in gamma, morphism. And what is a commutative diagram? Commutative diagram, as I said before, whenever you have two passes between two objects, you want that the composition of the map along the passes will give the same maps. And now I think it's probably makes sense to include also the empty path, so you just have one point, but you also can go like this. The empty path is the empty composition, so means the identity map should be equal to this composition. We will usually not draw such diagrams. And so usually when you draw diagram in a paper on a blackboard, and you don't say anything, you almost always think that it's commutative. But I will try to be careful and say the general diagram, commutative diagram, but they often probably not. Okay. So in the same way that we can discuss category, so over category, we can discuss also category of diagrams. Yeah, maybe for convenience, let's discuss category of commutative diagrams of a given shape. So if we have some shape like this, for example, so we can consider the category of all commutative diagrams of this shape. So such diagram of this shape is always commutative. Categories whose objects are diagrams of this. And morphisms are commutative diagrams like this. So this will be category of all commutative diagram of a given shape. And should I explain the definition of the category? And oops. And also you allow to fix some of the objects in the diagram and consider the category of diagrams of this shape with these fixed objects. Some of the objects are the morphics. And this means that in both diagrams we will take the same object. So the over category is the category of diagram of this shape when you fix the object in this. Commutative diagrams that looks like two copies. Like you have two diagrams of the same shape, so you can just put them one next to the other and connect them with arrows. So commutative diagrams of this shape with the two object fixed, this will be morphisms in the category of commutative diagram of a given shape. It's slightly harder to define the category of all diagrams of a given shape, not necessarily commutative, but it's also of course possible to do. We probably do it later.
Not need to
What?
be-
What?
I asked if, then your morphism is not something like one diagram to other ones.
It's a morphism in the sense. So we start with one. We have two diagrams.
Yes.
And then we want to extend them to diagram, which includes these two diagrams, but also these horizontal arrows, these arrows that connect any object in one diagram to corresponding object in another diagram. And this what is by definition morphism between the two diagrams. Answer the question? No? Okay, I will answer this question and go back.
Is the morphism between two diagrams reflect a 3D diagram like that?
If the two diagrams are 2D, then the morphism like 3D. So you add one more. But it's only on the level of combinatorics, so don't really.
Yeah.
And each of these, each between two diagrams, each fixed element has, the arrow has to go from one, this element to go with one.
This is better.
You cannot take an arrow from here.
No,
Doesn't
that's not the first.
Okay.
Yeah, maybe I should do more interesting examples of this. It's fun. Okay, let's do it now because this is the next example I want to give. Suppose I have two objects X and Y. And now I can consider diagrams that look how we want to do it like this. So diagrams of this shape with these two objects fixed. What does it mean morphism between two such diagrams? So where I have one diagram like this, I have another diagram like this. X, Y, so X and Y are fixed, and Z and Z prime are the same. So if X, Y would not be fixed, then I would have to consider maps like this. But now X and Y are fixed, so I don't need to do it twice. So I just do everything here. So I will put Z prime over here. Diagram morphism between two such diagrams is an arrow like this, such that this entire new diagram is complete. And now in this category, I fix two objects X and Y. I can ask what is the initial object. And this initial object, if it exists, is called the coproduct of X and Y. So here we have some very common abuse of notation. When we talk about coproduct of X and Y, we should talk about object in this category, meaning a diagram like this, meaning this. An object Z together with two embedded. But often when we say coproduct, we just mean the object Z. But with two maps like in the back of our mind. So it can be confusing. And since it's an initial object, this object is unique up to unique isomorphism. But where the isomorphism is isomorphism in the category of such diagram. So it's unique up to unique isomorphism. So if we have two coproducts, Z and Z prime, if they're both coproducts, can be, but then it means that we have isomorphism between Z and Z prime in this category. So it means isomorphism that makes this diagram commutative. And it's unique upon this condition. If you just ask whether there is a unique isomorphism between Z and Z prime, no, they're isomorphic, but there are many isomorphisms. Because Z can be have a lot of endomorphism, automorphisms, isomorphism from Z to itself. But in the correct category, it's unique. And this is also very typical in category 2. So now let's do example. And who wants to start with example of coproduct? Choose your favorite category and oh, this is this is tough choice. Yes. What is coproduct in the or at least not for community, for general it's okay, for general it's so let's agree.
Oh, you asked me?
Okay, I can answer that.
Oh, okay, sorry. An embedding of there needs to be an embedding of both planes into the such that
Doesn't really have to be embedding, but often it is. So we have two maps. Okay, we can leave it to I want to start with some easy example. So let's do the most basic example sets. Who know what is the co-product in the particular sense? You know, or you want to ask a question? What?
On the all the pairs, what you said.
This is very good answer, but for different question, which we'll discuss. So let's try. We have to set x and y. We have the product. What are the maps here?
So, okay. The map, yeah.
You kind of want to take any element from x and map it to x, comma, some x element y. Don't have such. So we even don't really know how to find it.
Yeah, so in the category groups, I can have that, yes, I that's it.
Yes, and then you can have these
Yeah.
maps,
And then
but it
unique
will
maps.
not be the co-product, but sometimes so you can modify it a little bit and then it will become. So it is over there, the answer, but was not for this question, not for now. So for sets. Anyone? Yes. I am in general comment if I ask last question, so I think some of you don't answer because you feel you already know the answer and it's not okay to answer. So if you feel like this, so you can count till 5 and then answer. So what is joint union? X, Y. What is joint union? So you just can take X and take. So when you talk about set theory, so each set is actual set. So maybe they're not disjoint. Yes, maybe the set of all people in this class and the singleton of myself that are not disjoint. So what do we do? Okay, so we just change one set to be basically rejected, but not like very nice set, which is the same as it, but with some time. So maybe it's the easiest way to define this joint union is I'll say you take x times a singleton of 0 and y times the singleton of 1. So it will be ordered pair when the first is x and the second is 0, and here ordered pair when the first is y and the second is 1. In this way, that certainly will disjoin, and then you take the unit. So we have this defined like this, and now we have two nice maps of x to here and for y. Is it clear what are the maps from x to here and y to here? And why it is initial object in the why it's a co-product. Want you want to say?
Well, they can. There is well, it's obvious what the map of the disjoint is.
Yeah, we have elements in X. And if the joint union, we want to map it to Z. How do we do it? If it's an X or comes from X, then we know how to do it. Just use this map. And if it comes from Y, use this map. And this is a unique way to do it. So of course there are many maps from here to here. But if you want the diagram to be commutative, it means that if you start with element here, you can go directly with this is the same. So element of X, you have no choice. You have to send it here. The element of Y, you have to send it. Well, so this is a disjoint union, and as you saw, I did some arbitrary choice here of how to make X and Y disjoint, and there are lots of ways to do this choice. So there's no one object which is a disjoint union of X and Y, but they're all isomorphic, and they're not just abstractly isomorphic, they're isomorphic as objects in this category of diagrams. Okay, so this is sets. What about vector spaces?
Because we can put the 0.
This is part of the way to work, so we can just define it. V W, V times W, or let's call it this. So you can put a 0, so you can define it, but you still have to say why it is initial object. So we have some thread. So why there is a map from here to here? The unique
Because,
map.
I could, and power decompose it as a sum of each instanted basis vectors and big level. All the components that are from this little B, they use the map from B to Z. So that we
Yeah. And you don't really have to choose a basis, so you can take any element here, and by definition, you pair V,
Yeah,
comma
it's a
W. So you know how to set V, you know how to set W, and the pair just tend to their sum. So the good thing you have in vector space is sum. So you can sum it. Great. So these work in vector spaces. Will it work in groups? Exactly. So you can start with the general group. So you can define the product, no problem. And you can define the map like this, embedding when you fix H. But now if you have new group set, you have two maps like this, you not necessarily have a map like this. Because here any element in G and any element in H commute. And here, a priori not necessarily. And so the images here, you just might have no morphism. So you will have no more than one morphism, but you might have zero. So product in group, in vector spaces, it is the coproduct, but in groups, it's not. And there is a reason why we call it coproduct, because the product in groups will be product, and in general, Cartesian product is usually a product, but coproduct is each time something a bit different. So sometimes it's called coproduct and denoted like this. Sometimes it's called direct sum. It's called direct sum when it's contiguous, where it behaves like a product, which we'll discuss in more. So any guesses in groups, what is the coproduct? What? Free product of groups. So what does it mean? There is this notion of free product. So it's a little bit complicated notion. So we start with the group G and H, and then we basically want to take both of them together, like do the union here, but allow to throw in whatever we get. So of course we cannot just take the union because with only one, the element one has to be the same. So you take all the elements in G, all the elements in H, but you consider the element, the unity element the same. But now you just throw in whatever you have to throw. So if you have G and H, so you have G times H. And now if you have another element, G2, so you also have this element, and it's different for anything else. So in general, you just consider long words, for instance, element in G, element in H, element in G, element in J, H. You consider the collection of all such words with some aspects, which I say in a moment. And product just means to concatenate them, put one near the other, and basically this is. Now you have to be a bit careful because when you say all such words, you need to first of all decide where you start. You start with G, you start with H, and where you end. So you can do, let's allow to start with everything. Good. Now, so all the words, so it means that they have in principle like 4 types, depending on where they start and where they end. Don't really matter. Don't really care. And now you don't want to allow to use identity element. But if you use identity element, you should be allowed to erase this element and then take the product of the others which are in the same group. So you're not allowed identity element. If you want to write identity element, you just write anything. And the last thing, what happens when you concatenate? You just put them one next to the other, but then you have 2 elements in the same group, and then you have to take their product. And or you might have 2 elements in the same group, and then you will have to take their product, and this product might be identical. And then you have to erase it, but then you will have another 2 elements in the same group, and then product again might be identity, and then you have to erase it again, etc. So the definition of product is a bit complicated if you say it like this. Another approach is say no, you always start with G, with element in G, and you take as long sequence as you want. And you can even say that you always finish with element in H, doesn't really matter, but you do allow phasing here. But now you have to say that there are some equivalents. So either you allow everything with equivalences, or you say no, you don't allow some things, and then you can find it. So in any case, this is a coproduct because this is an initial object in such diagrams. But each time we have this Z, we know where to send G, we know where to send H, and we know where to send each word. And a priori we could be afraid that maybe we will know where to send some word, but we will know it in two different ways and we will get this different elements, like in G times H. If it was G comma 8, if it was the usual product. So we kind of know where to send G comma H. We have to send it to G times H, but we also have to send it to H times G. So we have two options. But here, since the product is free, there's only one option because each element of the free product is just says complete instruction of where to send it, and each two different elements. Oh, sorry. Yeah, there is just one instruction of what to do, and then you just have a well-defined map like this, and it's a unique possible way to do it because the map has to be homomorphic. So, question about the free product?
Some problem. With the identity element, it's why can't you just take each identity element G and H, not the empty,
With the what?
the empty
word?
Yeah.
No, you can just. So you want to define the problem with the identity element is when you define the free product. So you have two approaches how you can define a collection of words, like distinct words mean distinct elements, and that's the way around. But then you have to forbid the identity element because G times identity H, yes, is the same as G. It has to be the same as G, yes. And these are two different elements of the set of words. So if you want the free product to be a set of words, you have to forbid some words.
But can't I just say that?
You can say that equivalent.
Yeah, the
Well,
identity.
So you can say the set of all either both identity elements are the same, it will not help you because still this word, even if it's the same identity element, it's not the same as the word G.
Yeah,
It's a different word.
so
So either you introduce equivalence relation quotient rate, or you just exclude this. So it's very common. Probably the best way is to introduce, like when you define rational numbers, how you define rational numbers. You can say let's define the expression of the type n divided by n.
except when I'm
Except n. But okay, but there is another problem. So we have a rational number 4 divided by 2. Do we have such a rational number? So probably the best way to say yes, we do have this rational number, is just equal to the number of 2 divided by 1. So rational number is not just an expression, it's equivalence class of expressions. But another cheaper way is say we don't want to think about equivalence classes. No, so this is forbidden rational number. We want numerator and denominator to not have common divisors. אמרתי את כל המילים נכון? So here I chose the cheaper way, and of course there is another way which is better. But what?
want them to be co.
So the cheaper way is to say that they are combined and like not taking identity analysis. So the cross product might not have a map to a Z that has such two maps. For example, if Z is a free product, there is no map from the cross product to the free product. Because the pair G comma H, I don't know where to send it. I have to send it to G times H, but I also have to send it to H times G. Okay. So now, oops. Okay, now I want to talk about product, but we can do it after the break. So let's finish co-product. Not yeah, co-product. We want some other examples. Topological spaces, there's the joint union. The vector spaces, there are some abelian groups. Product group. Because free product in the world of abelian groups is just a product because the saying that GH is equal to HG is not additional condition if we live in abelian groups just one. Here are some remarks that you see here. The abelian groups is full subcategory of all groups, but yet the notion of co-products is completely different. This is very common. Sometimes it's not different, but sometimes. So, for example, metrizable topological space, full subcategory of topological spaces, and the co-product is same. Sometimes doesn't change, but sometimes. Yeah, I promise you rings.
Yeah,
Commutative
if they're
rings.
commutative, then it's product, it's just a product.
No, because what is the reason why it doesn't work? No, the answer is tensor product.
Hmm?
The answer is tensor product.
That's all.
And why and product does not work. So, for example, because you don't have a map from the product to the tensor product. But from tensor product, you have a map to any link set. Include most of these things, but you know what it is. And this okay, so do you know who knows what tensor product? So almost everyone. So you don't need really technology, but if you know it, then this is where this is the result, and you can do the exercise to prove that you do with rings, and tensor product is the couple. The difficult one and all of them. And how to say it in English? Okay, it's an example. So another example that they gave they pointed topological spaces. What is pointed topological space? Topological space when somebody shows a point and say I like this point more than that. And what is morphisms of pointed topological spaces? It's just continuous map of topological spaces that maps a special point to the special point. So what is a cut product in the category of pointed topological spaces? You can do the same, by the way, with set. What is cut product in the category of pointed sets?
This joint union that identifies the 2 points.
Yes, exactly. It's called the bouquet of two topological spaces. So you can write them like in two axes. You don't have to, but it's not support. It's not like support. It's just put the one here and one here, and you do the one. Okay, so another, and maybe this time 10 minutes break. Okay. So we meet in 12:15.
ההגדרה של הקטגוריה שהתחלנו לדבר
הקטגוריה של דיאגרמות כאלה.
בסופו של דבר יוצא שהמורפיזם עצמו הוא גם אובייקט בקטגוריה.
לא. הקטגוריה של כאלה דיאגרמות של x ו-y הם קבועים. אני ניסיתי להגדיר את זה באופן כללי, אבל בואו נעשה את זה ספציפי בקטגוריות. זאת אומרת, אובייקטים בקטגוריות זה שלושות. Z, פי ופסי. מה זה מורפיזם של שתי אובייקטים? אז קודם כל צריך לצייר שתי אובייקטים. וניתן שתי אובייקטים, מורפיזם של שתי אובייקטים כאלה זה העתקה כזאת, כך שהדיאגרמה הגדולה הזאת כמו זאת אומרת, טק שווה לטק, וטק שווה לטק. עכשיו, אמרתי לצד אחרת, אמרתי דיאגרמות כאלה שהן קומוטטיביות, אבל אחרי שקבעתי את שני אלה, רק מידע, כל מה שיש לי רק שם. כן, מופיעים את זה.
צריך שזה יהיה אינישל אובייקט.
הקו-פרודקט זה אינישל אובייקט בקטגוריה של אובייקט. אז במובן מסוים את כל הבניות הקטגוריות אפשר לבסס על אינישל אובייקט. אתה עושה איזה שהם ג'אמבו מגדיר איזושהי קטגוריה, ואז אומר, אני רוצה את אינישל אובייקט. ככה אפשר להגדיר טרמינל אובייקט, שזה אינישל אובייקט בקטגוריה הפכה. קו-פרודקט, שזה אינישל אובייקט בקטגוריות גדולות. ופרודקט שזה קו-פרודקט בקטגוריה הפוכה, זה אינישל אובייקט בקטגוריה הפוכה, יש קטגוריה נפט.
כל מה שאתה עושה קטגוריה של גם אתה מקבל את התגובה שלו. כאילו מגדיר קטגוריה שמקבלת את הצורה של בין שני אובייקטים.
כן, אז קטגוריה של דיאגרמות אני תמיד חייב לקבל הצורה. לא שמעתי על קטגוריה של כל דיאגרמות בכל הצורות בעולם, ולפעמים אני יכול לקבע חלק פעמים.
ואז אתה חושב על הקטגוריה של פרופרודקט, אתה חושב על הקטגוריה של פרופרודקט?
אני... לא, קופרודקט יש רק אחד קטגוריה. אז זה קטגוריה של דיאגרמות כאלה. יש איזה שם, קוראים לזה לפעמים ספנג'י.
ככה אתה כאילו מגדיר...
רגע, אני עשיתי גם כל הפוך. ציירתי את זה של פרודקט.
אולי אתה חושב על האובייקט הזה?
אז כאן יש על המהות הזאת, שהרבה פעמים אני חושב על בעצם רק על אובייקט קטגוריה מקורית, למרות שבפועל צריך לזכור שהוא בא ביחד עם שתי שיקולים. אבל לשחקן הראשי זה אובייקט, ושני סקורים. כמו שאיך אתה חושב על מרחב וקטור. מרחב וקטור בעיקרון זה שלושה, כן? קבוצה, כפל בסקלר וסכום, אבל זה קבוצה, נכון? בדרך כלל אומרים יהי V מרחב וקטורי, אז אני אומר יהי X שייך ל-V, לא X שייך ל-V, אז הוא אחד משלוש הדברים בשלושה הזאת. לא, X שייך ל-V הוא שייך ל...
אז בעיקרון כאילו זה בא עם זה, אבל כאילו זה בא תמיד על השיקולים ואתה כאילו חושב על זה.
אתה משלם על זה בטל וכאלה נמצא. אני לא עושה את ההקלטה. אולי אני לא עושה.
אוקיי, טוב.
אתה רוצה לשאול?
ואז אתה כאילו, ואז אתה יכול לחשוב עליו כאובייקט בקטגוריה המקורית, יכול להמשיך.
כן, אני צריך לצאת בקטגוריה המקורית, אבל צריך להיזהר על זה, כי אז מישהו יגיד שהקו-פרודקט מוגדר ביחידות של איזומורפיזם יחיד. לא, איזומורפיזם זה לא יחיד, יש הרבה איזומורפיזם בין קו-פרודקט אחד לקו-פרודקט אחר, אבל הוא יחיד בקטגוריה הזאת. אוקיי, זה הבעיה בוויזואליזיישן.
אוקיי.
כי אנחנו רוצים שזה יהיה אובייקט בקטגוריה של פוינט פרודקט ספייס. השאלה הבאה יותר ולמה מוכר לנו, היינו עושים את זה קודם, זה לא היה קופרודקט, כאילו למשל לא הייתה העתקה לקופרודקט האמיתי, אבל אין את הקופרודקט האמיתי כי הוא בכלל בקטגוריה, ואין אף אחד בעייתי בזה אחר שבין שתי דקות כאלה שונות, כי העתקות תמיד צריכות להעתיק את הנקודה המיוחדת של נקודה.
אני יודע מה ששמעת מקודם, לא אומר שזה 100%, אבל אתה אומר בעצם שרוב ההגדרות אפשר להגדיר אותן, כאילו לקבל של הגדרות בצורה ספציפית, נשאר לקטגוריה של ההגדרות האלה, עם הצורה ספציפית הזאת, ואז צריך על מי שלא תקצון
כן, חוץ, אוקיי, קודם כל צריך גם להרשות להפוך את זה בקטגוריה יותר מנהל, אבל די, זה דירה ספציפית על קטגוריה אחרת. כן, אבל זה כבר, כן.
אבל אחרי שהגדרנו את זה על הקטגוריה מהסוג הזה, בסופו של דבר, זה לא משהו שלי בכל... זה לא סט. זה לא הקטגוריה של סט.
לא. אני מתחיל מאיזושהי קטגוריה כללית C, מסתכל בקטגוריה של דיאגרמות בסט. כן, הקטגוריה שנמצאה כאן היא לא בסט, היא באיזושהי קטגוריה C. ושם יש לי מושג של סכום ישר. של פה. עכשיו קופרודקט זה יכול לשאול מה זה קופרודקט.
אז ממש מגיע. לא, כי בקטגוריה הזאת יש לנו לא את ההגדרה בפרי. עובדת, אבל אם אני מתפסר משהו נצטרך להסתכל גם איזשהו חלק ממנו.
זה יכול לקחת לי אחד.
הכוונה שלי ש...
יש לו שתי קבוצות, זה קבוצה, זה שתי העתקות
עליהם נגיד, עליהם מאוד מכל שאר העתקות, כל שאר המורפיזם שיש וואי לזה. רק על שתי אלה ספציפיים.
זה אומר שהקופרודקט עצמו הוא לא יהיה קבוצה, הוא יהיה אובייקט בקטגוריה נקודתית. אבל הרבה פעמים אנחנו שוכחים למבנה וסתם חושבים עליו כקבוצה.
אני ממש מחפש את המבנה הזה בתור הקטגוריה של זה.
זה לא שאתם מתחילים טוב, אתם מתחילים מאיזושהי קטגוריה, זה שלושה, כן, זה קטגוריה של כל המבנים האלה. זה קטגוריה חדשה, שאובייקטים זה, זה, זה הרבה יותר אובייקט. אתה יכול לתרגל כמה... וההשקות ביניהם זה, יש שם דווקא פחות הקלות, לא כל ההתקלות. פרנט, זה פרנט תכלס גם.
כאילו, אפשר גם להגדיר את זה למודלים.
אותה הגדרה כמו שאני אמרתי עכשיו, זה לא הגדרה.
זהו, אני רק אתן, השתמשתי ב-wedge folder, cross folder, dot folder, זה בין כולם טכנית. אני הבנתי שאפשר את כולם. לא, differential forms. פחות.
מה זה דוק?
wedge folder.
wedge.
אוקיי, wedge folder.
כן.
אני חושב שזאת ההגדרה, זה משהו בדיוק שזה עובד, או שזה עובד. נשמע, כאילו זה.
טנס, כאילו אם טנס זה שונה, אני ממש בטנס יש כאילו 12 שוב מותרים שונה, אז אני חושב שזה לא, אני מדבר טנס פיזיקה.
אני לא יודעת.
בסדר, פיזיקה זה מעניין, זה... זה כדורות.
פיזיקה זה פשוט כמו מטריצה, מאוד דו-ממדי.
אבל יש לה פה דיפנדנט,
אני לא יודע מה ההבדל בין קובריאנט לקונטרוברנט.
אני עשיתי כמה קורסים בפיזיקה ואני גם...
כאילו זה רלוונטי רק כאשר אתה עושה יחסות כללית, כמו שאני יודע.
כן,
זה אומר שהעתקה ליניארית זה או שאת מגעת להעתקה עצמה או שאתה עם תוסף שנות בסיס.
אוקיי, בסדר.
לא שזה יש איזה משמעות.
לא, זה אומר שנגיד, אם יש לך קובריאנט וקטור פילד ואתה רוצה לשנות את זה, אתה רוצה לשנות קורדינטות, אז אתה משנה קורדינטות, אז כאילו זה לקחת
וכאילו סתם ככה אתה גם מזמן לקרוא, אז אתה כמו שיש.
לא, אבל זה נגיד, שהוא קונטרוברנט, אני לא יודע איך זה עובד.
אין לי שום הגבלה על זה? לא נראה לי. כאילו זה מרגיש לי מאוד מזרקי, כאילו מרגיש לי ש... זה דבר שכאילו...
אני עוסקתי רק עם התנסות פרטית, אז אני
מה זה שזה נוסף שיש לי מרגיש של וואי, ואז יש לי כאילו העתקה מזה ופה. אין לי שום הגבלה על ההעתקה הזאת. לא, כן,
זה המושג של מורפיזם בקטגוריה הזאת, והעניין של זה כל פרודקט זה אומר שיש כאן.
סבבה.
כאילו אם יש נסיעה באופן כללי בין שתי אובייקטים בקטגוריה הזאת, אתה יכול תמיד להוסיף עוד רפש, כן? אתה יכול תמיד לשים עוד 10 איברים בזה שלא קשורים לכלום, שלא נמצאים בתמונה, ואז אתה יכול לעשות מה שבא לך. אבל העניין של אובייקט הוא לא רק שאם יש יהיה רק אחד, אלא פשוט יהיה רק אחד. אם יש לי שלא. לא חייב. אוקיי, so will we continue? Yes.
רק אחד או שרק אחד
The initial object is unique up to unique. So, but the initial object by definition is the object such as any other object. You have a unique, really unique morphism from the object to Okay. Products. Products are co-products in the object. Yeah, so here is one really bad thing with all the names in category theory. So since category theory occur in different theories, then sometimes you start to study from one direction and sometimes for the other, and then you have weird names. So for example, here we start with start with co-product. And then we go product. So since the co-product is more basic, we call it initially it's kind of more basic than terminal, but co-product is more basic than co-product. So and in some maybe in the next lecture we'll discuss the notion of limit. And then there is a notion in general categories, there is a notion of limit and co-limit. And these are the new names, and the old names are direct inverse and direct limit and inverse limit. And then you can all guess what is the correspondence between new names and old names. And as you probably guessed, direct limit is co-limit and inverse limit is the limit. Because it's so this life and yeah, I am recording this and this will be. Okay. So examples of products. Who knows example of product? Product of sales. Guesses? No guesses? What's product? Gross product. Strategic product. We have to that's X and Y. So maybe I should I said what is product, but I said it in kind of non-direct way. Say product is a co-product in the object category and object and co-product is initial object in some other category. So now let's try to compile everything together and phrase object and product. We have two objects, a product is two objects, an object like this, two maps like this, such as for any other Z and for any two maps like this, they exist and unique map like this that makes it the other English definition of product. And now we see that if you have cross product and you have sorry. And yeah, because everything is self-category, so it's now terminal object in the category of plain flexes. Yeah. And so
all of the apples are now in the reverse order.
exactly, including this one. So why it's true? Why for sets you get different products? Because if you have an arbitrary set Z, which maps from Z to X and from Z to Y, then of course now you know how to construct a map from Z to here. Just take the first map, comma the second. You need to get the ordered pair and you have to map something. So, and this is work really well. So it works for sets, it works for groups, for Abelian groups, for vector spaces. It obviously gives you a lot of reason for topological spaces, pointed topological spaces, and rings. Am I right, doing? Yeah. Algebraic varieties, and here it's a bit more complicated because it's not obvious how to define the structure of algebraic variety and what's in the product, but you can also algebraic geometry, so it's also more so. So products basically all the examples that I can imagine now is just a Cartesian product. But of course it's very easy to construct as examples because it's the opposite category. And set product is co-product and then you get all variety of examples. It's okay. It's interesting to study both of these notions for poset. If you're a poset, then product and co-product is kind of a maximum. And in fact, not really a maximum, but maybe better to call it a supermum and infimum of the two sets. So a minimal object, which will be larger than each of them, is a product, is a co-product of two elements. If you have two elements poset, then object which is larger than both of them, but the minimal among all such strong minimal of all such objects, and it will be the co-product. The product will be the one below. Okay. And now the fun is fiber product. What is fiber product? Fiber product is the product in the over category of given object. So if I have an object X, I have two objects in the over category, then I can define the fiber product, which will be more compared to Y. X, which will be. So formally I should also write this arrow, object with over category, together with two maps, one to here and one to. But since this arrow is like not very new information, we can write it. There is just an object like this, and such that this diagram is commutative, and which is initial object among terminal object among all such objects. So if we have some other Z prime, this with two methods. This, then there exists a unique method. So this is a fiber product. And I always don't know how it's really called fiber product or fiber product. I think the more logical name is fiber product, but the more common name is fiber product. And so what do we think? Say the example of sets. Do we have any guesses?
There's a set and Y such that there are image and X.
Exactly. So in sets, with the collection of our pairs, the subset of the product, or collection of our pairs, Z and Y, is mapped to the same element. So this is a fiber product. And again, this construction works in many cases, but here we have some problem, and unlike product, which is defined in more or less any normal category that you are imagining, a fiber product is not so common. And the reason is that you have to solve equation. Yes, you take all the pairs that satisfy some equality, this kind of solution equation. So, and not every category has this feature of solving equations. For example, smooth manifolds. Yes, smooth manifolds you can do with a lot of stuff. You can take their product. You can write down the equation. You can take a continuous function and ask where this continuous function is equal to 0. The answer usually will be not very good. Somewhere that you can get some set, which is usually not enough, or maybe often not enough. Statistically speaking, it's 100% of the cases will be a manifold, but this is not really just 100%. And there's 0%, it will not be. So today, x times y equal to 0. This is a self-solution. So some places where fiber products are really large, these are algebraic geometry. Algebraic geometry is more or less by definition geometry that you can do with equations. So this is why fiber products are called very algebraic geometry, or I would say fiber product. So the like opposite object for the fiber product is the push out. Push out is the fiber product with object with category, and let's say you have a max like this. So we push out that you have two such maps, and this is the initial object among all such diagrams. So it will have the prime and two maps like this. And here I will not ask you to give an example of a push out even in sets, but not example. I will actually give an example of push out, but not a general definition. General definition is a little bit harder. We'll discuss it in a moment. But can you give me some example of push out in sets? So what? Co-product of pointed set is, yes, it is social set with respect to what diagram? So if you have point here, you have x, you have y, and you have, if it's pointed sets, it means that you can make an embedding. Now you can forget that they are pointed sets, there are two sets which happens to have such maps, basic set that was pointed. And then you can define a push out. And this would be exactly the push out, the co-product of pointed sets, meaning that you take x, you take the disjoint using y, and then you call the equivalence relation that this point here and the point here are the same. And what's really going on here? So what went on here? Here we take pair of like elements in the product and then put some conditions. So the two maps should be the same, so the diagram will become. So here we also can start with the co-product of x and y. But then this diagram will not be commutative. But just co-product will just have map here, but nobody forms as a diagram commutative. And here, in order to force the diagram to be commutative, we just took a subset to satisfy some condition. But here we cannot force the diagram to be commutative by taking a subset here. Here we have another way to force the diagram. How we force the diagram like this to be commutative? Before, we have like two maps from here to here and from here to here. And then what are the conditions? This have to be equal to this. Here we can't say a condition because this will be a condition on Z. If we want to change this set, we cannot change that. So what we can do instead of taking subset? Anyone? Exactly. We need to quotient by some equivalence relation. So we have two maps. From the, if we erase it over here, we take the co-product. This diagram is not commutative. We have two maps which are different. And now we can say, okay, we want to force them to be the same. So for any z here, we want to force 2 points here to be the same. So we have to put the relation and to take quotient by this equivalent relation. And in general, this is a solution. So a push out in sets is a co-product quotient by the equivalence relation given by the conditions that for any z, this thing is equivalent to this. But this is a big problem. Why is it big problematic? Because nobody promised us that this will be equivalent relation. So some simple solution, or the general solution is saying, okay, I don't care what this means not equivalence relation. It is symmetric or always can be symmetric, reflexive, whatever. But it's not unsplit. So we'll just make it unsplit. Just add more and more equivalence, generate equivalence. I mean, usually it will be less. But if here and here you have embeddings, then it's not good. Because then you have x and z is subset inside it. Think about embedding in one. So and think about the subset here, y and z inside it, and then you just say that the point is z here and point is z here is the corresponding point that you consider them the same. So push out is like glue. Yes, you take x, you put some glue on that's z. You have y, you put some glue on z and y, or you need to z and y, and then you just put some one on the other and line that to it. This is a way to see it. But if the map is not one-to-one, then you can start with some gluing lots of things to themselves and more things. We don't know where the gluing will end. Okay. And push out. Equalizers and co-equalizers. And they also can be defined at each object. Okay, but now I will do it manually. I have two maps from x to y. I can define the equalizer. Equalizer intuitively, if x would be a set, I want to solve an equation to say when phi and c are the same. So to find all elements in x, you are the same. But we don't have a notion of element general because x is just a name. Yes, internal structure. So we say in a categorical language. How do we do it? We consider the category of all diagrams like this, or formally of all diagrams like this. We have Z map to X, you have phi and C, and you want alpha phi, and the only close equal to alpha. So you can see the all diagrams, the size space distribution. I can't call them commutative diagram because I'm not computing. It's not equal. But you can see all diagrams, size space distribution. And among this, the collection of all these diagrams form a category. How do they form a category? So if we have del prime, alpha prime, so a morphism between two such diagrams is a map like this, such that this triangle I could not can be demand all the diagrams to be commutative, but it's not. This diagram is not. So in the collection of all the diagram of this type with this notion of morphism, I consider that initial term, initial object. So the initial object in the collection of all such diagram is called the equalizer of phi. And the equalizer is intuitively means a set of all solution of this equation, phi of x, and phi of x equals sequence. So is it clear what is an equalizer? And the dual thing, the opposite thing is a co-equalizer. So terminal object in the set of all elements exist with the same dimension. What is co-equalizer? Co-equalizer, it means that it's a quotient of y where you force them phi and psi to be the same. So where you glue phi of x to psi of x for any x. And of course, sometimes it will be really hard to do because sometimes it will not be a pure isolation, so we have to glue more and more. And I want to say something about yeah, so here is a nice construction where you basically can create equalizer and co-equalizer from product and cohort. I will tell about both. So if you have x and y and you have two maps, so instead of writing them like this, I want to write them. No. So I have two maps from y to x. So because of the definition of the product, we have two maps from y to x. I have a map from y to b to c. This gives me a map from y to x times. I do it. And if I have two maps phi and c, then by definition of the product, I have a map from y. No, I don't. So I think this is gives me a map. I have two maps from y to x. I don't exist. So by definition, it gives me a map from y to the product. So by definition of product, I have a map like this. Now another map that I have from y to from x to x times x to x times x is a map from x to x times x, which I call the diagonal. Why do I have this map? Again, from the same reason, because I have the identity map x to x. There it is here. So once I have these two identity maps, by definition, it gives me a map from x to x times x. So it's a unique map such that this diagonal is good. Why do I call it diagonal? Because if x is a set, then this map will be exact in the category of sets, any other reasonable category. It's a map that map point x to the pair x comma x. So the image will be the diagonal inside x times x. Now I have two maps, one from y to here and one from x to here. So I can take their fiber product. X, y times x over x times x. So this final product, I claim that this is exactly the equalizer of phi and x. Let's do it in the category of sets. In the category of sets, what is this map? This is just map each point y to a pair phi of x, comma psi of x. And this map point x to a pair x, comma x. So now we do pairs pointing y and pointing x, such as phi of x equal to x, phi of y, say, pair y, comma x, such that both phi of y equal to x and psi of y equal to x. So this means that those two are equal and that x is absolute because I can reconstruct it to form plus y. So it's just collection of points of y that maps to the same system. And here that exercise homework proof is that the equalizer indeed in any category, not only your sets, when the equalizer is isomorphic to this fiber product, and when I say isomorphic, so you mean that you have strict isomorphism, and of course in the original category C, this isomorphism will not be unique, but I think it just will be unique in the other category. But in general, the exercise is to characterize this isomorphism. Okay, so these are about equalizer, co-equalizer, and fiber products. Okay, there is another thing I wanted to talk about today, but maybe before this, I want to jump to a general overview of the course, so you will know what to expect. So I'm not expecting this to be a heavy course, so it's kind of infrastructural part of mathematics, category theory, and it's also interesting as a topic of its own. But the first thing that you do with category theory is just use the language to talk about other topics, right? And I think this is the most important thing that I want you to learn from this course. So we try maybe at some point dive a little bit deeper into category theory, but the general aim of this course is how to use category theory in day-to-day life in math. So the chapters will be like this. So today we'll still try to so each chapter kind of have planned to be one lecture, but I'm not sure it will work. So today we'll continue hopefully with these general definitions and examples like of the basic things. And next time I hope to talk about abelian categories. So abelian categories in some special class of categories that occur lots of times in algebra. So like category of vector spaces or models of an algebra. So some things where we can add stuff like abelian groups, for example. And yeah, so I would like to talk about them. Next time I will try to talk about that. Like the next chapter will be functors. So like if we have groups, we have homomorphism of groups, if we have vector spaces, and if we have categories, so we have to talk about map categories, and the notion of map categories called functor. And in a sense, you can just say that this should have been the first thing that we discussed, because we just try to advocate that if you have mathematical theory, you should think about the categories that this mathematical theory define. So you don't really care about internal object structure of the object, you just care about morphism between two objects. And so if they defined you a category and they gave you some complicated internal structure, I should have said what is the category of all categories. And yes, we can do it, but it's a bit complicated. So that's why we just going to lecture further. And we will talk about functors, which themselves is not complicated notion at all. But the category of all categories is a complicated and sometimes misleading object. Maybe I will comment about it today. So basically, this is the idea behind factors. So maybe, yeah, there will be 2 chapters about it. And maybe the most important outcome of all of the thing will be the Yonel dilemma. And Yonel dilemma is kind of giving you a posteriori justification of why it's okay to talk about category and not about the underlying theory. So when we talk about group theory, so groups and elements and notion of product, etc. And then we say, forget about all of this, we only care about the category of groups. So why you can reconstruct from just knowing the morphism from a single object or the other object, why in what sense you can reconstruct its internal structure. And this is what it's not, it's a bit circular argument because it gives you it in the language of category theory, but yet the bottom line of your lemma is that this idea is justified, that you can read out information of an object from just knowing all morphisms from this object to any other object, or the other way around, from knowing morphism from any other object to this object. And this can give you another approach to construction category theory. Instead of constructing an object, you just answer the questions. What are the morphisms between this object to any other object? And once you answer all these questions for all the other objects, from this information you can uniquely construct the object if it exists. And as we say here, the initial object, terminal object, product, co-product, fiber product, they're all unique if they exist. Unique up to unique. And this is another way to define all the construction in category theory by defining what are the morphisms between them to other objects. So the first stage, the first step, defining this morphism, always exists. So you always can say what you want from the object in terms of what are the morphisms. So it's like decompose the construction to two parts, and the first part it always exists, and the second unique if it exists, but not always exists. Next, we will talk about more categorical constructions. Maybe I should not go to such details. And then I will try to do some chapter on groupoids. So groupoids are slightly closer to the notion of group than general category. So you remember we talk about general group and generalization. And in a group, we let go two things. From group to category, we let go of two things: the invertibility of each element and the fact that all the symmetries are of the same nature. So if we just let go the invertibility, we get the notion of monomorphism. But if we just let go the idea that all the symmetries are of the same object, so we're still talking about category with many objects, but we remember the invertibility, we want also know invertible, then we get the notion of groupoid. So groupoid is somehow a bit closer to group, but from this categorical point of view, and in the same way that groups have kind of, this is the basic level, has much richer theory than monoids. So groupoids have much richer theory than general category, and we'll talk about groupoids. And yes, so I think at this point, this finishes the basic part of the course. It's planned to be like half of the course, maybe it will be, I think it will be more like 2/3 of the course, but just the theoretical plan. And after that, we can, I have some plan and you can see it on the website, but can give you other options. So I'm not really sure what we do after that. It's also maybe depends on you. And one of the reasons I'm doing this course this semester is that next semester we'll have a course in infinity categories, which will be given by Shachar Tomelin, which will dive much deeper and hopefully will expose that preparation for this next course. So infinity category is much newer topics than category theory. It's category theory probably started in the 30s and became very popular around the 60s. This is many branches of mathematics use this language, not necessarily to develop it further, just to formulate your statement, very convenient language. And infinity categories arise in the beginning of this century. So people was talking about them for a long time, probably as long as categories, because there is some basic flows in category theory that you see more or less immediately. So great, you have category for any theory, set, category of sets, category of topological spaces. So what about category theory? What about categories? And when you try to define it, you can do it, but there is some basic problems. And like I see already in 60, somebody defined the notion of two like higher level category, which the collection of all categories is not really just a category, it's a two category, something that so the members of the object kind of have higher level structure. But when you see this, you immediately understand something is wrong going on here. So by two categories, or what's the category for two categories? I'm going to make three categories. Then you ask what is the three category? And there was no really one definition. So there was several definitions, and there was those problem with it. And only in the beginning of this century, we kind of solve all these problems, and now we're more robust view of higher categories for n, for infinity, this of categories. And it's kind of harder than category theory. Category theory, I say, you can go dive into it, but you don't have to dive into it in order to use it. So in infinity category, you kind of have to dive a little bit, well, not a little bit, quite deep in order just to be able to use it in other theories. I hope it might change and you will understand better and better. And I think already now that we can take in the world that category theory had the last century, and hopefully in this century, infinity categories will have some standard for formalism statement, but of course it depends on the topic. But already now it's rather popular in many topics, not as popular as category theory. Probably how it was like 50 years ago, 70 years ago, 60 years ago. Okay, so this is about the overview. What I wanted to say about this lecture. Monomorphisms and epimorphisms in this lecture. But before that, any questions? Oh, this is a very good question. I don't really follow, but in the syllabus I list some books. But I didn't read them. I just heard from other people that they're good. And so I'm not sure that they'll probably be basically the same. I think the book will have more material than the course. Because like books in category theory usually kind of trying to dive deeper, and I want to give some examples, etc. But yeah, it's probably so. I think the book I got the best recommendation about was it's McLean book, category theory for working mathematician or something like this. But it does not include the theory of abelian categories. So for abelian categories, I give another textbook just for that. And so this is about like the basic part of the course. The last third we will be more. More questions? Oh, so let me say what a monomorphism, and then maybe I will say some more. I don't know. Before monomorphism, I want something else. Let's redefine the notion of so in many textbooks, you will see a different definition of category. Instead of talking about a set O and a set of morphism for two objects in O, we will talk about pairs. Set O and set more. And O will be the set of all objects in the category, and more will be the set of all morphisms in the category, not necessarily from two given objects, just all of them together. Which looks a little bit weird because we can't really compose them, yes. But then we have two maps for more to O. That's for each object in O, for each morphism, says what is the beginning, what is the source of this morphism, and what is the top. Now, once you have this information, you basically can reconstruct everything. So now we talk about morphism between two objects, just morphism that source is one object and target is another object. But now we can use a categorical language and the notion of fiber product in order to define the notion of category. How we do it? So we take more, we have source, and we have where we start with that. And we have top. So what is the fiber product of these two sets? everything is set, so we don't really need to know category theory, but we do need to know the notion of fiber product, which we can define for sets without knowing anything, but it's kind of natural when you do. Not exactly, because here we have target and here we have source. So we have morphism here and morphism here, and the target of this morphism has to be equal to the source of this morphism. So these are exactly pair of composable morphisms. One end where the other begins. More, or maybe we'll just call it more two. So pair of composable morphisms, we will define with more two, by definition will be the fiber product. And then when we define category, so we want two sets, more and log, two more maps, source and target, and a composition map which start not with more times more, because we can't just compose any two of them, but start with more two pairs of composable morphisms, two more. And this is of course no, yeah, you start with more, and yeah, we need to say something about the source and the target. Okay, now we have to write down, if you want to do it fully, then you have to write down all the axioms. So there are lots of axioms here. For example, when you take composition and then you consider the source is the same as to go to here and then to consider the source. So I can't write in commutative diagram, so this diagram is not commutative, but you can do first this and then source is the same like projection to here and then source, because it's a source of the composition and the source of the first morphism. And again, the same with the target. And now we have to talk about the associativity, which we can also write with diagrams like this, or just say element wise that the position is associative, meaning that if you have three maps, which such as the first two are composable and the second two are composable, and then the composition is associative. For objects. So we can write all the axioms before in this language. Those two languages are completely equivalent. The advantage of this language that you can try to play in any category. So instead of working with category sets, you can talk about category of topological spaces. So more will be topological space, or will be topological space, source and target will be continuous map. And then you can play this game and define a category with additional structure of another category, in this case of topological space. So this language is kind of more categorical way to think of the notion. So this is one thing I want to comment. And now another thing that I want to comment is about the category of categories. So we will define the notion of functor, which we basically made with, and this by itself defines the notion of category of categories. But this is kind of a bad notion. So you can work with it, you can define stuff, but you often will get misleading things. Because inside a category you have objects, and you can ask whether two objects are the same or not. So technically you can talk about equality. But practically you don't want to do it, because as we already saw, yes, we have the Cartesian equality. There is no one object that is Cartesian. There are many objects that are all isomorphic, but they are not equal. And if we can say, okay, never mind, we can define for sets, we know what is the product. Ordered pair. Okay, then we can ask whether the Cartesian product is associated. And it's kind of clear that it has to be associated, because we know it's the same, it's like three parts. But on the formal level, if we have three sets, the Cartesian product is not associated. It's not the same. Talk about the ordered pair of these two things is not the same pair like this. So these two sets are not the same. And so talking about quality in category usually can give you better results. And this is why talking about quality of also functors which are like kind of morphic in between categories also give you bad results. And so the collection of all functors between two categories is a category by itself. And if you can't think about the set, it might be a problem because it's a large set, but let's go it. And so you can think about it as a set, but this is misleading because different elements in this set might be isomorphic, and you want to think about them as the same. And the first place when you see it is when you talk about equivalence of categories. So if you have two equivalence of categories, is an analog notion for isomorphism of objects. So if you have two categories, you can say when they are isomorphic, when there is functor from here to here, functor from here to here, such that the composition is equal to identity. But saying that they're equal to identity is very strong demand. It's saying that if you start with an object here, go here, and then go back, you get the same object. And this is usually will not be the case in almost any algebra structure. Usually you get isomorphic object. So just knowing that it's isomorphic is not enough. You want to have this isomorphism to demand some thing about this isomorphism. So there is a notion of isomorphism of categories, which is rather bad, and then there is a notion of equivalence categories, which is much more reliable. But if you consider the category of all categories, there will be only one notion there, just isomorphism in this category, which is two space. And this is the reason why the collection of all categories is better to consider it not just as a category, but as a two category. And some framework that allow you to ask when morphisms not only equal, but also when morphisms are isomorphic. But we can talk about morphism between morphisms. And so the notion of two categories is not very complicated. We'll try to talk about it both, but when we try to go further to higher notions become more complicated. Will be done next semester. Okay. So now I'm run out of time, so monomorphisms next time and the big entity goes next. Thank you very much.
Sounds good.